Designing the physical aspect of the car was also challenging. It started out with the Raspberry Pi along with a power bank to power it, two DC motors, and a battery pack to power them. However, the DC motors were unable to bear the weight of both a power bank and a battery pack. Hence, I tried using better motors by using EV3 Lego motors. To do this, I cut off one end of the wires and connected them to the Raspberry Pi via a motor driver. However, this too was to no avail. In the final design, I added the EV3 brick as well. Now, the Raspberry Pi gives commands to the EV3 brick. The EV3 brick also contains the 6 batteries needed to power the Lego Mindstorm's DC motors. The EV3 brick is able to efficiently manage the DC motors and hence the car drives smoothly. There's only one sensor on the car and that is a camera. Originally, an old first generation Raspberry Pi official camera was being used. However, its field of view was too narrow, so I have now upgraded to a 120-degree wide angle camera. Now, onto the brains of the car. In the main file, an SSH connection is established with the EV3 brick and the web camera is initialized. We are now ready to go. We start in the while loop. Over here, a new frame is read from the camera and saved. Then we pass on to get hidden. In get hidden, we first run object detection to see if there are any traffic lights, stop signs, etc. using YOLO V8. This YOLO model has been fine-tuned on our own custom data. If there's a need to stop, then the code terminates and returns back to the main function. Otherwise, it continues to get lanes. In get lanes, the image is first cropped. This prevents the robot acting too much in advance, as in it turns now for a future turn. The image is then converted to grayscale and we perform thresholding to remove noise. Thresholding converts the image into a black and white image. This can now be fed into half lines. Half lines returns line segments from the image. However, there are often multiple overlapping or same line segments. Hence, they are merged. After being merged, we need to tell which two lines will be our lanes. To do this, we have the pair lines function. The pair line function checks for various parameters such as distance between the top, distance between the bottom, their angles, etc. Using these parameters, we can tell which two lines will be our lanes. However, if we are not able to extract any one pair which works as a lane, or if there are too few lines, then we have to try for a single lane. This can also often happen during turns, where during a right turn, the right lane goes out of frame, or during a left turn, the left turn goes out of frame. In this case, our head-end is reverted to the angle of the line. However, this can often be too steep, and so it is not taken in full, but multiplied with a coefficient. This function in the end returns a pair of lines or a single line along with a head-end. This head-end is now returned to our get head-end function. Head-end, we feed it into a PID controller. This ensures a smooth path. The final value after the PID controller is fed to the EV3 brick and the entire process starts again. This is how the self-spy car runs.